All right. So, well, thanks very much for the invitation. Thanks for squeezing me in. I mean, I thought that,
It's great. It's great to hear.
And I had a different title. Then I realized I saw the names of the people and the talks and everything, and thought, okay, maybe I changed the topic. I still could talk about that. Was related to heavy tails, and this is also related to heavy tails. But I thought, okay, maybe this is probably going to be interesting. And I think it does relate to Geronimo's problem at the beginning. And okay, so a lot has been said about rates of convergence to Markov chains. So let's see if I can say something new and interesting. Okay, so this is joint work with Yan-Lin Chu and Peter Glynn. So Yan-Lin is a student who is on the job market this year, and this work is supported by a joint grant that I have with Alex and Gareth. So I'm happy to show that we are doing work. Okay. All right. So so the point is rates of convergence of Markov chains by using the Wasserstein distance. And so part of the motivation is studying rates of convergence in operations research for very, very large queuing systems and algorithms that are, data-driven training with a fixed amount of data, constant step sizes, stochastic gradient descent. Okay, so well, the motivation is to study doing with the Wasserstein distance because, surprisingly, well, the total variation distance is what you learn, and I will review the techniques. But for these types of problems, total variation distance doesn't quite actually work well, and so that was kind of part of the motivation. So we are going to investigate how fast X1 converges to the stationary distribution, and I will motivate and I'll hopefully kind of introduce some new tricks, and we'll go from there. So first, I'm going to start, kind of motivating the total variation versus Wasserstein. I'm going to review later, the standard technique to obtain convergence in total variation. And the standard technique to obtain convergence also in Wasserstein, and the standard techniques kind of follow a similar pattern, and then we are going to try to just break that pattern a little bit and see what good things happen after you do it. So so the sort of standard technique that we use to obtain convergence in total variation involves in general, a state space Markov chain, so for continuous spaces, involves two elements. One is a Lyapunov function or drift condition. So this goes back to the paper of Jeff Rosenthal, but many others have done work with that, Peter Baxendale and Garrett and here in the audience.
So you want to have convergence, geometric convergence?
No. I'm gonna do general. I'm just reviewing the geometric convergence.
Because lambda times v, it's.
This is for geometric convergence.
Yeah.
But that's not. I'm actually going to emphasize this sort of issue of partitioning the space. It's kind of too brittle, especially in high dimensions. And so the idea is, you want outside of the space to converge to sort of visit. And then once you are in some small set, you want to generate some sort of coupling. And that's kind of the standard technique. And these bounds tend to be very conservative because you require, for example, in these kind of systems, the whole queuing system or this very, very high dimensional system to altogether sort of be out in some sort of complex set. So it kind of works like this. You have your bound. This tells you, this gives you a bound on an exponential moment of the time to hit the set C. And then you have two chains typically to measure these bounds. One starts with stationarity, the other doesn't. And then once you are in this small set, you can couple them using this sort of condition. Sort of how does it? That's how it works. So you have a geometric number of trials, and there is for this sort of thing you kind of like want to pick the set C small so that you can have a nice beta, but then you want to pick a set C large so that you want to kind of have a large lambda, and this tension makes things pessimistic typically.
Do we have an explicit rate based on lambda and beta in general, or is it?
Based on lambda and
Yes,
beta,
yes,
there is,
yes.
there are examples, hard to obtain them, okay? The point of this talk is to obtain stuff that is very, very new. This is a paper that we published at the end of last year. And I hope to convince you that it's much easier and more practical. The numbers that we get actually are things like 0.9, 0.7 per multipliers, things like that. Uniform in step size, stuff like that. So,
Nice.
okay, so the drawbacks in total variation, I mean, as I say, like in the infinite server queue or very, very large queuing systems to get convergence, you typically have to kind of empty the system. And that is, the total variation distance actually is not uniform in the arrival rate. Whereas most of the, you would intuitively think there is enough mixing and, it should be uniform. Well, in Wasserstein, it's uniform if you decide you pick the right metric for the measure value process. Something that, it's maybe a little bit surprising is if you train with fixed data set, if you train your machine learning model with a constant step size stochastic gradient descent, that type of algorithm will not converge in total variation. It's just because, this is a very simple example. You have a quadratic function, you just have Bernoullis, and the recursion is exactly like this for, any alpha, but in particular alpha equal to 1. This will converge to a uniform distribution, but it's impossible to have a minorization condition. So this thing is not going to converge ever in total variation. So this total variation is just not the right way of analyzing rates of convergence to stationarity for stochastic gradient descent when you have finite data set. It's just not.
But if you have spread out condition on this.
No, but you don't.
In this case, no.
Yeah.
No, don't.
Or additionally, you had like some
You
noise.
need to have noise.
No noise, you make smooth noise.
Yeah, like with density.
When you add the smooth noise, then something really funny happens. You decouple, so that thing, of course, you're going to get a rate of convergence in total variation, but it's going to depend on your bandwidth or your noise, right? Which is completely artificial because this is a beautiful Markov chain. This thing is going to converge exponentially fast, right? So, and in the end, why total variation? If in the end you are going to evaluate this in a continuous function, Lipschitz function, maybe even a smooth function, why measure it in total variation?
There are reasons.
But what about?
I don't understand the reasons.
So for instance, if you are working on like differential privacy, if you get
Yes.
a bound on like total variation, it immediately gives you some rate.
But this is a very, very specific application.
But
Most
it
of
has,
the
I mean, there
applications-
exists.
Yes, but I would argue that there are just okay. You're giving me the exception, not the.
But-
I mean, we are mathematicians here, so.
Yes.
What about epsilon?
Sorry.
Epsilon coupling.
Oh, you can do that, but
Yes.
right. I mean, you can have that, but it's going to,
You have total, yes, for epsilon and neighborhood, it's okay, it's done.
right. Yeah, but you don't have minorization.
You don't care. You do something. There are two conditions. The first one, you have to arrive.
Right.
Positive recurrence. And then what to do in a small set, you can do whatever you want.
Yeah, if anything that is a total variation for these types of chains, I mean,
No, you want to do about Wasserstein, do it Wasserstein.
right. Yeah. No, I mean, I think, yeah, well, we can talk about that. And so I basically kind of say, okay, my point of view is that in many applications, in queuing, I probably say in 99% of the applications in queuing. And yes, I mean, there are some applications, I guess, in learning, but it's I think it's just.
I would be totally agree with you if you replace solves by may solve. One of the ways to solve.
No, this, I mean, that's not, this is still proper English, right? If this solve, it's a, the solution, it might not be unique, but it still exists, right?
Categorically.
Yes. But maybe it's like, this is the elevator talk, it's my accent. So anyway, okay, so here's another way of doing the Wasserstein distance. You apply, I mean, there is a kind of like a standard way of doing it in Wasserstein distance. It also reduces to this problem of coming back a small set, and instead of coupling, then you induce a contraction. That is what you're saying. That's exactly what you're saying. And the problem is still this small set type condition. When you do that, then you have this, the Wasserstein distance, by the way, is this defined like this. Okay, so well, this is just the definition of the Wasserstein distance for some maybe not seen it. It's just is the minimization of all couplings given a cost function that preserve the margins. This is the optimal transport cost between mu and v. When the cost function is a distance in some metric space, in a Pauli space, then we observe the Wasserstein distance. When this is the typical distance we're going to be using the talk. This distance is always bounded. This recovers weak convergence without any moments. And if I use this particular distance, then it's total variation. So in principle, what I'm going to be doing, could be done even for something that is almost total variation if I approximate by a concave toss. I'm not going to talk about that. And as I say, the way it works typically is, you come back to this set and you want to contract this. Okay, so I said before, the dilemma when you try to apply these types of things is that you want the set C to be small if you want to have a good sort of contraction, and you have the set C to be large if you want to have good return, right? So the set large is going to be very quickly to return because it's very, every set C is large, is big. Then the contraction might be very poor. And in this example, for example, in a stochastic gradient descent, when you inject noise at this heavy tail here, you are going to have the set, you have to make it very small to actually have good contraction. So these two things don't play nicely with each other. Queuing recursions typically, kind of look like this. A stochastic gradient descent looks like that. The more complicated recursions, you can do all of them. Well, most of the time they look like that. So they are Lipschitz. And if you want to impose kind of Lipschitz properties on your recursion, typically they are very easy they are very natural to assume. So it makes a lot of sense to kind of impose conditions that have to do with the Lipschitz properties of your map here, and that's what we are going to leverage on in the results. So I'm going to introduce some notation. So this is fine. So all of these recursions then can be written as iterated random functions. So these fn's are my random functions. In this case, fn is going to be, in this case, f of x is just going to be x plus z positive part, and z is a service time minus an interarrival time. So similar here. And what we're going to be assuming, I'm going to be using this notation from now on. This f is going to be a random function, and they are IID, which means that's the same as saying that these z's are taken to be IID, for example. Okay. Okay, so now I'm going to tell you how that project really started. This project started from a paper that I wrote with a student, Xin-Yun Chen, in the context of analyzing rates of convergence to stationarity of high-dimensional reflected Brownian motion. So you take reflected Brownian motion on the positive orthant with oblique reflection. That's a very common topic, process that arises in queuing because it approximates workloads of general Jackson networks and heavy traffic. And we were able to show convergence to stationarity in Wasserstein distance using basically the following type of analysis, right? So we look at the derivative of the process in continuous time, and that satisfies a multiplicative recursion that is of this form. And intuitively, well, this is under the synchronous coupling. So start from the initial condition and apply just these iterated random maps. And if you want Xn to converge weakly, then Xn, of course, should forget its initial condition. That simply says that this DN process, that is, this product of random matrices, should converge to zero. And the speed of convergence of this should capture the speed of convergence in stationary. And you actually have, a very explicit expression of the Wasserstein distance, an upper bound, because you have an explicit coupling between the chain starting at any initial condition y, comparing to any other initial condition. You can start with the initial conditions being the optimal coupling in Wasserstein distance, if you want, of the stationary distribution in your initial condition. And literally, this process gives you a bound that is exact, right, for this. So, okay, so the idea was, so as I say, this was shown to prove reflective Brown motion with this uniform stability condition has relaxation time that is logarithmic, polylogarithmic in the dimension. So the challenge was, okay, so when we started talking about this with the student and with Peter, I mean, I thought, okay, let's kind of try to see if we can generalize this. Well, the problem is that, when you do this kind of thing, you are really in the realm of kind of the product of random matrices. And then you study the Lyapunov exponent, and this is not just independent random matrices. It can get hard very, very quickly. And so also we realize, okay, maybe this sort of things maybe do not contract all the time, maybe sort of contract sometimes. And how do we introduce geometry in such a way we can control the geometry or change the norm so that you can get contractions, right? So the way we did this was, okay, so we look at a very interesting paper by, I'll say Steinsaltz in 1999. Well, that was, Jan Lin looked at that paper. And we sort of went around the problem of working on in D dimensions, and sort of we look at a specific constant that is defined as the Lipschitz constant, right, of the random map. So we look at this local Lipschitz constant. This is something that in these examples in queuing and in stochastic gradient descent, this can be computed explicitly. And we, based on this constant, we build a theory that is based on this constant. So this basically is the Lipschitz constant of the random map. And so this is a random field indexed by X.
And is the difference between this and the Diaconis' result is this is local? Is just
the Diaconis is the Friedman, and the Diaconis paper is global, right?
Yeah. So
it's
this
global
is
thing.
the
So the Steinsaltz actually generalizes that, and this stuff. I'll show you the Steinsaltz result. The Steinsaltz result implies geometric bound. The result that by choosing U, I'm going to be able to obtain polynomial, semi-exponential, everything. And yeah. Okay, so this is the contraction. This is what we introduced. This is your drift condition. Okay, everything will follow from this drift condition. We're going to make assumptions on the drift condition, and we're going to define an intrinsic metric, intrinsic to this drift condition, that is controlled by this U. By the way, B and U are positive functions. Okay, so there will be a metric and an interplay between the metric, the Wasserstein distance, the geometry of the space, and this condition.
And this expectation is just with respect to the random function, yes?
Yes, there is the only random thing is F. Yes, indeed, correct. Yeah.
And do we need the domain to be compact or something, or is
No. This is a complete metric space, not even RD. Okay, so to give you an intuition of what this is, a Lyapunov function in the end. I mean, you can, if you add the Z, the noise, and the X, the recursion jointly, they also form a Markov chain. And this is just a function of the noise, right? And this is a function of the chain. So this is just a big Lyapunov function. And we know that when we have Lyapunov functions, we know what, what is it that they bound. Typically to just get what a sense, how to build them and what do they mean. We solve for the equality and that gives us a lot of intuition. So in particular, when you solve for the equality, it's not very hard to convince yourself that this V of X is precisely this summation. So you have this product of the different Lipschitz constant times this U, and that's what this Vx is. And when you if you place equality by inequality, then the Vx becomes a bound on this, right? So you have V will be greater or equal, and then when you iterate here, then you get the bound. V is larger. Okay. All right. So now, in a minute, I'm going to define to use something. You're gonna see that there will be bounds that are gonna look like magical because they're gonna be look really, really simple, and they are going to be involving some metrics. So so I'm gonna tell you. I'm going to make an observation here, and once you see the metrics, you're going to realize what, how is it that the proof techniques kind of should work, and what's the connection to the metrics. Here are some important some kind of, observations that are well known. I mean, if I take these maps, Xn, right? This is the Markov chain. I start from F1 to Fn. Yeah, I can call that Fn. I can, this is a very standard trick, right? You can just swap it back, and you have this F bar n, and typically you have that these X bars converge almost surely, whereas the Xn's converge in distribution. Right? When the map is monotone, turns out this is the optimal coupling. This actually gives you the optimal Wasserstein coupling. Yeah. So you don't need to really have contraction. Monotonicity also, suggests that this is a very, very useful coupling. Not always. You can come up with examples where the chains actually are running around each other. So here's another observation. Like if the chain rule applies to this Lipschitz coefficient as well. So you can take the Lipschitz Fn, right, and this is like a derivative. So this is like the product of the local Lipschitz coefficient. So you can see. This is popping up here. Now, when I look at this time reverse process, right? When I look at these XLs, these iterates form a path. They start from X0, and they are jumping in the space, and then they will converge to this X infinity. So they kind of they form a stochastic path. So this summation, right? If I add over this particular realization, this random path, and I multiply the x0, x1, because of this property of the Lipschitz constant, this is an upper bound. This summation here, where I have the infimum over all paths that connect x0 and x infinity, and I have this I kind of just embed this in a trajectory gamma, where the dk is precisely this xk. So this is, if I take this serves as an upper bound. When I take the infimum over all paths here, then I have this d of the distance between f1 and different consecutive things.
Could you remind what was capital F bar?
Capital F bar is this. So it's the iteration.
Okay, it's the product. Okay, I see.
Okay, so this turns out to be a very, very, very key observation. Okay, so this thing times dx0 x1 is an upper bound for this object here. Okay, now this infimum, when I take infimum over all gammas, that defines a metric. And so that metric is going to be an intrinsic metric, intrinsic to the drift condition that will allow me to get very clean bounds on the Wasserstein distance. So for example, this is the diachronics of Friedman result. If you have this global contractive drift, you get you get the Wasserstein distance decreases 1 minus r to the power n, and you have this beautiful constant here that can be computed between, just one step transition of the chain. This is the Steinsal result that introduces this notion of local contracting grip. He says, okay, let's not count this is too strong, let's do it just locally. And then he gets this representation that kind of looks a lot like this, except that this constant, changes a little. Okay, this is still very nice, very tractable, right? And so, yeah, so this was the departing point of what we did. Okay, got questions? I'm gonna come back and review this.
Xn on the left-hand side in this Wasserstein.
Oh, extend to infinity. Yes, thank you. All right, so, okay, so then what we did was, okay, so let's, basically the starting point, the very first result that we try to obtain is, wouldn't it be nice, like if somehow it was possible to have a correct distance, right? I mean, to write this as Wasserstein for the correct distance, whatever that is, x, and this is the distance in the ambient space, infinity, that's equal to 1 minus Rn, and then expected value of d with the correct distance, right? This is the d bar in the ambient space, x1, less than R. No? It will be kind of very pretty, like if this actually was the right result somehow. Yeah. Turns out this is actually what happens if you define the metrics in the right way. Yeah. And the key is precisely this observation. So once you see this, the obvious conjecture is pick u equal to v, and because that will correspond to rv times v. So this is, if you write rv minus v, that's 1 minus, so what's that? Yeah, 1 minus r. Yeah, so your v is u in this case. So that indeed is what happens, but many other things happen as well. So now you see, when you read the paper, you are going to be presented with these metrics, and they appear kind of like magical, like you define this basically this trajectory of against like any paths, and then you so this is the you are integrating final Lebesgue integration, and this when you plug in g equal to 1, basically you recover this LT. But in general, you can have any metric, and this would be precisely the sum, the infimum, right? The infimum, and then you have this f of g of gamma tk. Gamma tk, and then b of gamma tk, gamma tk minus 1. So this is how this metric, this is the same metric, now just speaking g equal to b. So the results take this form. So when you have this particular, for the polynomial case, if you have a drift condition that is, you have this v and the u and v are sort of conjugate of each other, and you have a contraction for u, right? Then you have, something that is a very clean exponent. If you think of b as integer, so then this simplifies a lot, and you have, the product from k equal 1 up to b. This will tell you that in this case, you have a polynomial rate of convergence in the Wasserstein distance, that is n to the 1 minus b immediately, times something that can be computed based on just one step transition. Okay. So I'm gonna later on kind of use it, but the point is that it's a very clean expression. This is how the result of a Steinhaus looks like in this particular case. So you have indeed, you have this condition, the metric dv actually gets you something that looks a lot like the result of Steinhaus. If you have, based on this contraction condition, now you have something that converges sort of like in between polynomial and exponential, like Weibull type convergence. So this sort of approach allows you to get everything in between, not only polynomials, some exponential, and geometric. So in fact, this result, this bound is stronger than the Steinsal's bounds. To see how. First, an observation is that this distance is smaller than this dv distance because this is the minimum over all gammas, and you have the triangle inequality here. So Steinsal's assumes that b is greater or equal to 1, so this is smaller when you plug in something that is larger than 1. And then, obviously, if you replace v by the maximum over 2 points in the trajectory, the end and the beginning of the trajectory, by something, anything in the middle, that's a larger number than just this dv. So then you have, this, though the Wasserstein distance with the standard metric in the metric space, like the d, is smaller than this Wasserstein distance with this metric dv. This is our result right here, and this is smaller than this part, which is where the Steinsal's gets. So this kind of is the right result. Something that's the correct extension of the Diaconis and Friedman. So it gets, it implies that one. That's very clear. Yeah.
So in terms of like stochastic gradient descent, what would be like an intuitive understanding of this dv distance? Like what kind of distance it's measuring? Like I
will give you the example. So it's going to depend a lot on whether the function is strongly convex, is not strongly convex, do you have finite variance, infinite variance, all of that, enters the choice of B. So I'm supposed to finish in 5 minutes?
Or whatever. We can no, 10 minutes.
Okay, so I'm going to show 2 examples. One is a queuing example, and another is stochastic gradient example. And the queuing example,
Actually 15.
15? Okay, maybe. Okay, so then, okay. All right. So in the paper, we introduced 2 techniques to develop these sort of things. One we call the large M technique, and the other one we call the boundary removal technique. The large M technique is useful for queuing problems are the harder problems because you actually need to use both. You have the boundaries are a pain in the neck. So we want to remove the boundaries, yeah. And so I'm going to illustrate that technique with the GG1Q. But actually that technique is required for the stochastic gradient descent example. So this large M technique, basically, you have a similar situation to this small set business where you have the local drift contraction in the Lipschitz is constant. Local Lipschitz constant is contracting for a small x, and you have kind of like your Lyapunov function outside the small set. So you do have the correct this quantity less than v, right? But only outside this small set, and you have something that has the expected value of the drift is strictly less than 1. So the one way to patch this sort of thing with this sort of technique is very easy. You simply need to add a constant to the function. This quantity here is going to be m times a number, so like m divided by 2, for example, is whatever that number is. And so you pick m large enough, you're going to enforce this equality for all x. Right? That's the point. And so this, once you are done, this Vmx is now your Lyapunov function. And the way we do it is we do parametric m, and then we optimize m at the end. So when you do this kind of thing, for example, in the G1Q, you know, if you assume that Z plus Z, the service times, say have n plus 1 moments, we know that the Wasserstein distance, using the distance xy equal to absolute value x minus y, that's gonna converge at rate little of n to the power n minus 1, right? Because you knock on. No, because it's Wasserstein, not total variation, right? So you kill another power. Yes. So this actually, you know, kind of captures that only with moments assumption. So that was a test. Now we kind of, all of these are small things. In the paper, we have larger dimensional problems. But the point is that you get kind of constants that are nice and you know, computable, like, you know, 5, 10. And by the way, what we are doing now is using neural, you know, basically learning V and U using neural networks. And so you don't have to actually even do it. So this is another kind of result. This relates to what you talk about. This is a situation where you have a sequence of problems like in heavy traffic. So this expected value of y has a finite mean zero. So you subtract delta. Delta is the constant step size, and in the stochastic gradient, and the y will be your noise. So this is a bound that is uniform in delta, and this is a correct bound. So it will be uniform rate of convergence of the stochastic gradient descent, uniform as the step size goes to 0, and along the sequence. So that is something that you can do with this type of technique. Okay, so in terms of, let me just go and give an example. This is a queuing thing. Yeah, so this is the sort of thing that you were asking. Like, for example, in this context, the sort of type of V that you need is this V of X is like 1 minus X put required. If so, this is not a strongly convex objective, and the U in this case actually turns out to be constant, but you need to pick the constant in the right way. Okay, so this, you know, in these types of examples, it seems polynomial V's seem to work well. So this is an example where again this once again captures the behavior that you should expect. If M is strongly convex, then in this case M is equal to 2 here, so you have alpha, and this will be order 1 minus alpha to the power n, which is exactly what you expect with a strongly convex you know, rate. If this is not strongly convex, if M is, you know, 3, 4, 5, then the rate of convergence should be smaller and is reflected by precisely the increase of the step size. You know, this becomes closer and closer to 1 discount. So this is also done with this M-large technique. This is another situation where you have infinite variance. And so in this context, you know, you have the same V is a polynomial V that is chosen with respect to this gamma parameter.
So, sorry, what is Z here?
Z is okay. So this is a good point. Yeah. So I think I went too fast because I don't want to bore people, but this is perturb gradient descent. So really, you want to do the following: main of this, and what you are doing is xn plus 1 equal to xn minus alpha h prime x, and you are injecting noise here. All right. So it's PGD, perturb gradient descent. Yeah, this is the examples that I'm studying here. These are baby examples. The paper is really kind of teaching the new method and how to use the bounds. I think there is a lot to do, you know, to make it in more kind of higher dimensions. But we do it for queuing examples. For the queuing examples, we do analyze stochastic networks that are grown, you know, in high dimension. So this is this is one example where you have so you have this something that is you know, this is not even, you know, you lose convexity, and you have a strongly convex around the origin, but the function is not convex, and you have infinite variance. So in this case, again, you obtain these polynomial bounds with this technique. So I'm not gonna, it's, look at the paper, I'm just trying to advertise. All right, so, the takeaways, I think, I hope to have convinced you. I mean, I think we are saying something quite interesting, new ways of obtaining rates of convergence that are flexible, obtain bounds that depend only on first step transitions. So they utilize, I think, the geometry of the space. You build the geometry in your Lyapunov function, and it integrates an intrinsic metric to the Lyapunov function that you define, and that is the way in which you measure the Wasserstein distance convergence. And this extends of sort of simplified, more generalized and simplified versions. Actually, I think that's a nice story of how it works. The paper discusses a wide array of examples in queuing, parametric, simultaneously in number of moments, and heavy traffic or step size. And I think this technique is showing promise to give bounds that are quantitative, useful in these types of settings. So that's it. Yeah.
Can you also get lower bounds? I saw some result where you had.
So sometimes you can get, not for this method, but as I said, like in the case of monotone chains, this coupling is exact. So you get that's a lower bound. So, but no, I mean, in some cases you can, but it's not due to the result. It's just because.
Oh, yes, I understand. No, it's hard.
Is perhaps a similar question. How do you know that your bounds are sharp?
Oh, in the queuing examples, we do know because they are monotone. So you can compare against the best possible coupling and right. Yes.
So thanks again to